Let's talk about buffer capacity. We've mentioned this before when we were talking about how to make a buffer. Buffer capacity tells us how much strong acid, loose hydrogen ions, or strong base, loose hydroxide ions, a buffer can compensate for without seeing a large change in pH. So you have to sort of think about this equilibrium we've been talking about and how it's affected by the introduction of a strong acid or a strong base. So in an acid buffer, we have our weak acid HA in equilibrium with H plus A minus. Now, we've got this. We put a salt in there. We put an acid in there. So we have some loose acid and we have some loose anion in there. And they're just kind of hanging out. Now, if I dump in a bunch of strong acid, I'm dumping in loose hydrogen ion. So can you see that this hydrogen is a different color? Yes, you can. So I dump in that loose hydrogen ion, the purple hydrogen, and what happens is that purple hydrogen will react immediately with the A minus in a one-way street, and it makes purple HA. Does that make sense? That when I dump in loose hydrogen ion, it immediately reacts with the anion and it makes some weak acid. Then equilibrium restores itself. But we have to think of this happening fast in a one-way street, otherwise the math gets too crazy. So we think of any loose hydrogen reacts with the anion, makes HA, and then equilibrium restores. Now, when we think about this, is this hydrogen ion any different than any other hydrogen ion? Absolutely not. But the reason I drew it in a different color and drew this in this step like this is that often my students get confused by this and they're like, well, isn't that just the equilibrium? Well, yeah, it is. It's the same species and the same chemistry. But in order to understand the math, if you think about this extra hydrogen grabs some of this A minus and it makes more HA. Then we restore equilibrium. Okay? What happens if I dump some hydroxide in there? Well, if I have this buffer situation and I dump in some loose hydroxide, that hydroxide is going to go ahead and grab free hydrogen ion. I'm sorry, that hydroxide is going to grab the HA, the weak acid, in a one-way street, and it's going to make water, HOH, plus A minus, in a one-way street. And then equilibrium will restore. So, in our buffer, if we add acid, which is H plus, strong acid, we make HA and we use A minus. Now, Andrew, this is for you because you told me you like me to write on the board. So pretend I'm writing on the board, but since I'm videotaping, I got to write on the paper, okay? So when I dump in strong acid, which is loose hydrogen ion, I make weak acid and I use up A minus. Does that make sense? Okay. When I add a base, a strong base, I'm essentially adding hydroxide. So I use HA, and in the process, I make A minus. Okay? That makes sense? Now remember that the pH of a solution is dependent on the pKa of the acid and that ratio. So, when I'm using up one of these and making the other, I'm shifting that ratio a little bit. But if I were to dump that free hydrogen ion or that free hydroxide ion into just a beaker of water, I'd see a huge shift in pH, right? So this minimizes that, and we'll see the minimal effect that it has in a few minutes. Let's talk about what happens in a basic buffer. In a base, we have our chemistry going on, our base chemistry. B plus water is in equilibrium with BH plus hydroxide. So, if I dump in some proton, I'll dump in my purple hydrogen again, it's going to immediately react with the base B in a one-way street and make BH plus with the purple proton in that conjugate acid of the weak base. If I dump in some base, if I dump in loose hydroxide ion, that hydroxide ion is going to react with what, class? What's the hydroxide going to react with? The BH plus, the conjugate acid, in a one-way street, and it's going to make the base plus more water. HOH. Yeah, I'm just drawing it this way so you see that this hydroxide is now in that water. So, in the base, if I add loose hydrogen ion, if I add strong acid, which is loose hydrogen ion, to a basic buffer, then I use up the base, B, and I make BH plus. If I add hydroxide, a strong base, then I use BH plus and I make the base B. So that gives you an idea how a buffer works. If I dump in a strong acid, it reacts with the conjugate base that's in the buffer. If I dump in a strong base, it reacts with the conjugate acid that's in the buffer. It doesn't matter if it's an acid buffer or a basic buffer. You get the same thing, it's just that we've named these species different things. So now, let's go ahead and look at how this all comes together in an example problem. Consider an acetic acid sodium acetate buffer that is 1.5 molar in sodium acetate and 1 molar acetic acid. Well, start off with the easy part. What is the pH of this buffer? Well, this is page 1637. So we know that pH, it's after the buffer thing that you told me you didn't like the bead activity, so. Okay, pH is equal to pKa plus the log of A minus over HA. Now we could use an ice chart, but I like this better because we're dealing with buffers, it's quick and dirty. So the pKa of acetic acid is 4.74 plus the log of the A minus, that's our acetate, 1.50 molar over the acid, 1.00 molar. So pH is equal to 4.74 plus the log of 1.50. So that's 4.74 plus 0.176. So the pH is 4.92. Now remember, we're used to dealing with the concentrations in terms of molar concentrations. But right now, we're looking at this ratio. And remember that when we're looking at that ratio, the ratio of the molarity is the same as the ratio of the moles. So if I have 1.5 molar divided by 1 molar, I get a ratio of 1.5. What if I had 1.5 moles in 12 liters? 1.5 moles per 12 liters, and I divide that by 1 mole in 12 liters. What's the ratio? It's the same, right? It's 1.5. So in a few minutes, I'm going to show you how we can shortcut by just using moles rather than taking time to find the molarity. Okay, the ratio of moles is the same as the ratio of molarity. And in some of the upcoming problems, you're going to see me take a shortcut. All right, what would the pH be after the addition of 50 milliliters of 6 molar hydrochloric acid to 2 liters of this buffer? So now, 5 milliliters, what? 5 milliliters of 6 molar to 2 liters of the buffer. So we have to go through a series of steps. We start by finding the number of moles of the acid and the conjugate base that are in the solution. Then we calculate how much strong acid or loose hydrogen ion is added, and then we can find the pH. So we start off saying first thing we're going to do is find the moles of HA and A minus in my solution to start. Need to stop the video here, it's getting too long.